Yo, what's up? This is Physics 2211, Lab 3, Black Holes and Orbits. So, uh, here's your table of contents. You got finding the mass, the fundamental principles, experimental design, the computational model part 1 and 2, calculation loop, and then our what ifs, and then error. The purpose of this lab is to analyze the motion of a mass given star to determine the mass of the black hole. And in part 2, we're using the mass of the black hole that we derived from the previous part to calculate the initial velocity of a spaceship that intends to do a figure-8 orbit around a star and moon. In the calculation loop, we calculated the forces acting on the planet and the spaceship. The main result of the lab is to demonstrate the effects of Newton's second law and its relationship with momentum. I found that the mass of the black hole was 1.12 by 10 to the 34, and the spaceship velocity ended up being about 20,000, and then the moon speed times 1.1. The fundamental principles here are the universal law of gravity and Newton's second law. We use the position update, velocity update, and the Newton's law of gravity. So here we can take our normal velocity update and we find that the change in momentum over change in time and derive from there. We get Vf equals Vi plus At. Um, Here we have Newton's second law modeled in circular motion, where the parallel component p hat is parallel to the direction of circular motion and it changes the speed of the object. And the perpendicular component n hat is perpendicular to the parallel component, and it points toward the center of the turning circle, and it's related to the change in direction of the object. And you can see here that all the components that go into it, into the derivation for F net, which is mv squared over r. The gravitational force on due into another object is described as F equals g m1 m2 over r squared times r hat. G is the universal gravitational constant, and r hat is the unit vector pointing from one mass to another. So here's the free body diagrams. You have part 1, which is the system is just the star, and the surroundings of a black hole in space. You can see the only force acting here is the force of gravity pointing here. Part 2 is the spaceship, moon, star, planet, the surroundings of the black hole in space. So the surroundings play a part on the spaceship and the sun, and then there's the sun and the spaceship playing on each other. So here's part 1 of the glow script model. You can see that here's our initial conditions. Star was given, the star mass was given, and then our XY velo was used with the seed. This is the seed right here, just my email, whatever. The next part was to find using these that we don't touch, and then to do the calculation loop using our X velo. So I made some FNet arrows so we could see the perpendicular components of it, and I did the mass of the black hole to calculate it. So it calculates it approximately based off of FNet and the radius times 2, or radius squared. So we just use that formula. Here's what I end up getting when I run the code. So I run it, and this is what we end up getting. So you can see the arrows pointing in that direction, and you see the mass popping up here. So I took that mass, averaged it, and I used that as my mass of the black hole, which ended up being the value described earlier. Part 2, we take our initial velocity and final velocities, which is going to be updated, and same thing with all the other stuff. And so we plug in all the values for FNet perpendicular, which is dp dt parallel, parallel, and then perpendicular is dp dt minus dp dt parallel. So the Fnet equals dp dt perp. So the Fnet equals change in magnitude of the momentum. Then we find Fnet on the moon. So we have to account for all the different parts right here, and this is where we account for it. So here's all the gravitational, the universal law of gravitational calculations, and they all account for every single force. These are the results. So you can see it's not a perfect figure 8 model, but it does stay relatively around here. So that was pretty much the results, and you can see that all this weird orbit is caused by all the different forces acting on the spaceship, not just the black hole. Otherwise, it would be a perfectly circular motion. Some possible errors in this are approximations or rounding errors made for each iteration. Since it was a simulated calculation loop, it can't represent reality perfectly, so there's bound to be a mismatch in some way. This error could explain the differences in masses between each loop. The accuracy was also affected because the trial and error method was used to find a decent orbit track. So obviously there's some better velocity that's way more lab specific and much better. For our what ifs, for part 1, what does it mean? The analysis should focus on distinguishing between the net force. So the net force is the total force acting on the object, which can be decomposed into parallel and perpendicular components. The parallel component changes the magnitude of velocity, thus affecting speed. The perpendicular component changes the direction of velocity, influencing the object's trajectory. Rate of change of momentum is given by Newton's second law. F net equals change of momentum over change in time. P equals mv. But the key distinction is that the parallel rate of change momentum affects the speed, and the perpendicular rate of change momentum affects the direction of motion. The net force and the rate of change momentum are equal by definition, but we have to measure forces directly to infer the momentum changes. If the net force is entirely perpendicular, it remains constant, but the object turns. If net force has a parallel component, it accelerates or decelerates. For part 2, predicting the mass of the black hole, The essential factors were gravitational forces, dominant interactions, and orbital dynamics. For gravitational forces, every object must exert a force on another object following the universal law of gravitational constants. You must track these forces on every other body. For dominant interactions, the black hole's effect is the strongest. The star has a strong effect on the planet and the moon, and the planet dominates the moon's motion, but the moon still affects the planet. For the orbital dynamics, the moon orbits the planet, which orbits the star, which orbits the black hole. So you need to model the center of mass and perturbations due to the gravitational influences. Thanks.